Is everyone here now? Okay, again, welcome to Biostatistics. And we're going to go over the one sample t-test, looking at our own data on class height. So we're going to start by looking at our data, right? Let's go enter our data. How do we do that? Actually, let's start by looking at the worksheet. Let's start by looking at the worksheet. So I'm going to share my screen, and can everybody open up the Lab 4 t-test class height worksheet that I sent you? Yeah? And I will say, share screen, share screen. Okay, great. Great. So here's our lab. Here's our lab for today. We're going to go over the one sample t-test and use our class height data to compare with a national average. So when do you use the one sample t-test? There's a lot of different statistical tests. This is the first one we're looking into. When do you use it? When's the right moment in time? You use this test when you want to compare a sample mean with a specified or hypothesized value, right? So you have a sample, you have a part of the population, like us. We're part of this bigger population from the United States. And you have this hypothesized value, you have this national average. Or let's say you wanted to compare your blood pressure with the blood pressure of people in general, sort of the normal. Or an example that we looked at in class, you want to compare a sample. Let's say we took a sample of all of our body temperatures and we compared that with the accepted 98.5 degrees. Does that work for us? Are we that? This is how you basically have a single one sample and you compare with a hypothesized mean. So the instructions for this class are to look up the average height of people you choose. Now you can choose a country or a region and compare with our average class height. We're going to do this one time together. I already looked up the average human height from the United States from Our World in Data, and I'm going to go to that website here. Our World in Data, does anyone know this website? Have you looked at it before? I love this website. I think it's great. There's so much great information on here. It's all about data, history of human height, the last 2 millennia, increase in human height over 2 centuries. I mean, there's tons of cool information. And I found this one here where we look at human height for women in the United States. It's women who were born in 1996, so adult women today, because you might imagine that would vary based on the year since it changes. So that's where I got this number, 163.54 centimeters. So women who were born in 1996 on average are 163.54 centimeters. So how does that compare to us? Assuming we're a random sample of people, which we may be, we may not be, there's some bias to our estimation. We're all people who occur in a particular region, but there's no systematic bias that I know of that would say that our class would be different than the national average based on what? I don't know. So I think our sample can count as a random sample. So I took this number, and again, this lab is worth 10 points, and you'll upload the assignment to this La Lima assignment tool. So the assumptions of the t-test. First of all, for the t-test, we have to assume that the observations from our sample are independent. That means the measurement of one student height does not depend on or affect the measurement of the height of any other student, which I think is a reasonable assumption here. We assume the heights are a simple, random, unbiased sample from the larger population. So in this case, the larger population is adults in the United States. It might be a little bit different because maybe our Our ages are different than this sample was from people born in 1996. I think most of the students in the class were born later than that. So we might see a difference there, but it's pretty close. We also have to assume that the height measurements are numeric or quantitative, which is true, right? Height is a numeric measurement. And we are going to assume that we have to assume that the population is normally distributed. So if the population is normally distributed, then this test is valid. If it's not, it might not be, but the t-test is robust to deviations from normality. So even if it's not exactly normal, we'll probably be okay. The first step is to state the question, the null and alternative hypotheses. So what's our question here? How could we phrase this? We could say this in a number of different ways. We might start just say really simply, the simpler the better, the more clear the better. Is the average height of students in our class different from the national average? And we should be more specific. We're going to say of female students in our class different from the national average. You could also put this in a different way. You could say, is the average height of female students the same as the national average? Either way, it works the same. And the null hypothesis, however, are stated very specifically. You could say, there is no difference in mean height between students in our class and the national average. That's the null hypothesis. In other words, you could say the mean heights are equal. The mean heights are equal. The sample mean from our sample and the population mean from the website are equal. Another way of saying that is that if you subtract one mean from the other, the difference would be 0. The difference in means is 0, right? The difference in means is 0. That's 3 different ways of saying it, but they all mean the same thing, and that all works, right? The alternative hypothesis is just the opposite of the null hypothesis. There is a difference in average height between our class and the national average. Or another way you can say it is that the mean heights are not equal. Or you can say the difference in means is not equal to 0, is not equal to 0. If you subtract the national mean from the class mean, it's not going to be 0. It's going to be something more than that. Is it? We don't know. Literally don't know. Okay, now we're going to find out. Step 2, collect the data. So now let's go to our class data Google Sheet. Go to our class data Google Sheet. Class data Google Sheet. Where's our class data Google Sheet? Oops, here's my Biostats plan. Show you everything. Great. Okay, oh, look at that. We got so many heights in here. Good job, everybody. Hey, what a great class. We got a lot of people here. Frida, are you here? Can you enter your height? Veda. Yeah. Emma, we need a few more people. Come on, we need to get a good sample size here. Ariel, Mia. And this is how we're going to take attendance too. Easy to take attendance. We know we're all participating because we're entering our data. This is what I use for the class participation verification. And these look right. It doesn't look like anyone accidentally put their height in feet because I don't think anybody is 161 feet tall. I have a feeling I might be an outlier, but maybe not. I'm probably going to bring down the average because I'm really short. If you've met me, you know that already. If you haven't met me, I might look taller on video. Maybe not. I know, Shelby, you're like, yeah, you're really short. Okay. Anybody else to enter your data? Come on, let's do it. If not, we'll just accept it. This is what we have. All right, we have 2 values missing. Maybe they're just not here today. So let's go ahead and download the data. Did anybody have problems using the Read Excel last time and was never able to figure it out? If you were, you can download this as a CSV file. I used Read Excel before and that worked for me. So, but I'm going to show you how it looks as a CSV file. I'm going to say download with comma separated values .csv. It's still a spreadsheet. It's just a little bit different version of a spreadsheet. And where does that show up? You got to pay attention where that shows up. Here, it's showing up over here in my class, in my downloads folder. Okay, now here, everybody heads up, pay attention. I'm gonna give you jazz hands, like give me your, look up here. If you can see this, you see how in my downloads folder, it says class data / class data parentheses 1. That's gonna mess things up. Change that name to just class data in this step. If you don't do it in this step, you'll have to fix it later, which you can, but it's better you just fix it now. Call it class data. And now we'll go over to our R Studio. And now you've already got all the code. This code was already provided for you by me. And you're all able to open it up, right? Open it up in our studio and you get this lab4 t-test class height rcode.r. Please raise your hand if this is not working for you. You got a couple hands raised back there, Michelle?
Yeah.
Okay. If you tried to download this from the Laulima assignment, it might have come up a little different. It might have come up as a text file. It might have come up looking something like this, right? You might have found it was a text file. You're like, oh man, that looks not good. Just copy and paste the whole thing into a new R script. Don't put it in the console, that won't work. If you copied and if you tried to download it and you got a script file, you got to say file, new file, R script, and then paste it into that new R script. But if you're able to just open it up as an R script, then it should be fine. It looks like this. All right.
Stuff we just did, like the one we just saved.
Give everybody just a sec here.
Like the cost data, or if you're putting it in here.
I can't even figure out how to download it from Laulima.
You can't download what from Laulima?
The thing that you're
the
talking
R
about.
script? Don't get it from Laulima. Get it from the email I sent you. It'll work better. That's what I'm saying. If you try to get it from Laulima, it's probably not going to work. If I go to Laulima and I do it, I'll show you what it looks like. It looks weird. That's why I sent you an email.
Yeah, so this is normal, so it's just showing me what you just downloaded.
Okay, so if I go to my assignments, and I go to class height and see what this looks like. So if I look at the student view and I see, okay, oh, look, there it is, right? There it is. And I try to download this, right? This is what it looks like. You're like, oh my God, that's not right. No, but don't worry. It's okay, Brianna. We got you. Just take all this, select it all, right? Just select it all, copy it, Control C, or how you do. Go back over to go to your R Studio. And if you did it like that, you won't have this, right? So you're just going to say File, New File, R Script, and you're going to have a blank one. Then just paste all that gobbledygook into here and it'll come out looking just like this. It'll be fine. All right, and just save that. Does that work?
Yes.
Yeah, I got it. Thank you.
Awesome. See, we did it. Yay. Okay, cool. I knew that would happen. This is the first time we're doing this. It's all good. I don't need to save that. I've got this over here. Make sure you save that. You're going to need that script. So t-test one sample, student height lab. If you've already installed the Read Excel and or the readr packages, it's easy to then load the data. So you've downloaded the data, right, from the Google Drive, either as a CSV or XLSX. Either way looks fine. And you go over here in the upper right-hand side where it says import data set. And there's this lovely little arrow with the drop-down menu. And it says either from text base or from text reader. Now I downloaded my data as a CSV. So I'm going to use this from text reader. If you downloaded it as an XLSX, use Excel. But I'm just going to show you what it looks like with the reader. So with the reader, it looks exactly like it did when we did with the Excel file. You browse to your data. Where is it? I've got it over here in downloads. You might have it in downloads too. Class data. And then it's going to give me a data preview. I can see, oh, here are all of our data fields. That looks okay. I've got height comes out as a double. That's good. This is the code that it uses to import the data. I'm going to copy and paste this code and actually put it into my script in case I need to do it again. And you probably can't see if you're covering it as being covered up here, but there's this little button on the bottom that says import. So just use that. Import. Okay, now it worked. And you can see here's the data that was imported as a spreadsheet. And you can see it over here on the right in the global environment. If you use this little blue arrow, which I think on a Mac, you don't have that blue arrow, but it shows you all the data fields that we have. And it shows that we have height and it comes out as numeric, which is good. That's what we need, right? So here's the tab showing the data. And then here's the tab for the code. So we'll come back here to the code and I'm going to paste that code that I got from that import step in here in case I need to do it again, because this will just be like faster. It's fewer clicks. I can just run this like, right? And then if you need to rename the data, this is an optional step. If you didn't change your data name, when I tried this before, I also had this problem where it came out as class data, class data. If your data is not named class data, type in the name of the data that you actually got. Like look up here on the right and see, what does that data say? Does it say class underscore data? If you did, that's fine. You can skip this step of renaming the data. If your data are named anything else, type in the name of whatever that is and run this line and it'll rename it to class data. I'm going to skip this step though, because I already changed my data name. It's already called class data. Everybody good there?
Yes.
Yeah?
Would you be able to go over how you got the class data again? I missed that. Sorry.
How I got the class data into R?
Yes, please.
Okay, so how I got the class data into R?
But this
All I
looks right.
did was I went up here in the upper right-hand corner where it says environment. You see where it says import data set. And there's this drop-down menu here. Did you download your data as a CSV or an XLS?
I'm not sure. I just downloaded whatever was on the email.
Okay, no, but the data you don't download from the email, the data you download from the Google spreadsheet. You got to go to your Google spreadsheet, right? You go to the Google spreadsheet where you entered the data.
I copy
Here?
and pasted off of Laulima because I couldn't figure out how to.
Okay, but the data are here. The data are on a Google spreadsheet. I sent you an email with the link and we've already entered data in this, right? Can you get to the file? Looks like you entered your data here, so you got your file, right? You're here, right? So you're in this. You're in this. Watch, just watch. You got this. Will take 1 sec. Everybody will get it. All you do now that you're here is you go to where it says file, and then where it says download, right? And if you choose download comma separated values, it's like raise your hand if I'm blasting too fast. But if you don't say anything, I'm assuming you're with me. All right. Comma separated values. And now what's going to happen is that's going to drop this file into your downloads folder. It's going to drop a file into your downloads folder. And what happens for me when I download it is it comes out being called class_data/class data and then 1 because I already did it. I'm going to delete this one. Change that file name right now, or you can change it in a later step. But if you change it here, just change it so that it's called class_data. Raise your hand if you're confused. Okay, now you got the data? Yeah, okay, great. Now go back to R. Go back to R. And now you do this data import step. You go where it says import data set from text read R, right? Because we downloaded it as a CSV from text read R. And that's going to bring up this dialog box, which is super easy. You've seen these things a million times. You're like, where's the file name? Oh, just browse. Browse for it. Go to where it is. Again, for me, it's in the downloads folder. So I just double click on it from the downloads folder. You good? Yes, okay. And here are the data. Now, I also copied and pasted this code on the bottom and I put it into my code. That's optional, it's up to you. The important thing is that you see it here, you see height is here, it's a double. We've got all of our values here and you just click this button that says import. Boom. And now it's there. Now, does your data say class data like this, or does it say something else?
It says class data.
Okay, perfect. If it's exactly like that, then you're good. And it should have come up here automatically, showing up as a spreadsheet, right? Now go back over to the next tab, and here's your code. You got your code up already, right? Yes, you got your code. Okay, you got your data in, you got your code. You're super good to go. I mean, you can skip this step of renaming your data because your data are already called class data. Now we can go on to the important step of cleaning the data. And I like to talk about cleaning the data because I know that this is a really big part of data analysis. And unfortunately, a lot of classes actually like skip this step like it doesn't even exist. They just they give you a canned data set and the data are already perfect. And they're like, here's the code, run the analysis. And you're like, oh, okay, this is great. I got this. And then you go to actually work with your own data and it's a mess. And you're just like, it just doesn't work at all. Because you need to clean your data first, always. Data cleaning can be half of the time of data analysis. So I'm always going to include a little bit of that. In this case, it's pretty simple. We're just kind of prepping it in a way, right? We're just prepping it. And the first thing we have to do is we need to select just the females. Because if we include the males in there, it's going to skew our data. Remember, we're comparing with the average female height. Find anywhere online that had human. I just found males and females separate, so we're going to have to analyze it separately. So to do that, I wrote this code for you. And the first thing we got to do is, okay, you look back at our data here, you see how we have with sex, right? Remember we went over this before? How when we entered the data, we did it in a very non-standardized way. Some people wrote capital F. Some people wrote lowercase f. Some people wrote female with a capital F. Some people wrote female with a lowercase f. R will take these as 4 different kinds of things, 4 different categories, but we want to have them all as one category, so we need to make them all the same. We could either do that by changing the spreadsheet, or, and this is better data practice because it provides transparency, right? Everybody can see what you did. If they have your raw data, they can see step by step what you did. You didn't fudge anything, right? You made it clear what you were doing. You go back to your R and you run this little step here where it says to lower. What do you think this command does? To lower, class data sex. Oh, this changes all the letters in that column to lowercase. That's step one. So just run that code. All you have to do to run the code is you see that your cursor is on that line and you either select run, which I usually avoid because I like to use my fingers and not wear out my mouse finger. And I hit Control Enter and it runs that line. You see that it sends it down to the console line. And now if you actually looked at our class data, you would see that it's all now lowercase. It's all now lowercase in here. In here, it didn't touch the original data. That's safe. It just changed the data in R. So we go back over to our code. And the next line here is we're going to change everything that says F to female. So it's all going to be female. So we're just going to run this line and say wherever you look in, we're saying R, look in class data sex column. And where in there you see it, where you see either F or you see female, change that to female and stick it back in that column. That's what this code does. Where did I get this code? ChatGPT. Yes.
My data didn't change to lowercase f.
Same.
It didn't change to lowercase f when you did this first line.
Yes.
Try running it again. And you look at it and it's still not lowercase.
It's still the same.
Did you have an error message?
Looks like I'm doing the exact same thing that you are doing, but then it doesn't.
Right.
change
Did
my
you get an
data.
error message? Down at the bottom, was there any red?
No.
No. What's your
The same thing's happening to me. I've run it quite a few times and there's no errors, but it's not changing anything.
Okay, so just to make sure we're all, but you do have this, you do have class underscore data is the name of your data set, right? Right? And you do have a field called sex with a capital S, right? Right? Your data look just like mine. And you run
Yes.
this, and it's not changing it.
Yes.
But it's not, you're not getting any error message down at the bottom.
I'm having the same problem, but I have an error message and because the object class data is not, but I have that on the side.
Right, if it says class, that's the error I would expect. It's saying class data not found. That's because, look up here. What does this actually say? Does it say exactly the same thing as this?
Okay, I got it. Mine is good now.
Yours good now?
Only that's different is that it has a capital C, not a lowercase. That's the only thing that's
It
different.
has to be exactly the same. If there's an uppercase or a lowercase, it reads it differently. And that's why I would expect to have an error message is if your class data didn't have the same name. But Brianna, it sounds like you're getting a different problem.
Yeah, I don't know if like she was able to figure it out, but my name's the same, everything's the same, and I've run the code like 6 times and there's no error message, but it's not changing.
There's no error message, but you don't see the change.
I ended up having to close the data set and then in the console reopen the class data set and then it fixed itself.
Okay, so you closed it. You mean you closed it here?
Yes.
Oh, okay, you closed it there. And then you ran the code. And then if you click over here, it opens it again and you see it and it changed.
Yeah.
Okay, Brianna, you want to try that? Try that.
See, because it has the same numbers. You're good, yeah, so just do the right worksheets. Thank you.
Just close it and open
Okay,
it
yeah,
up
that
again.
worked.
That worked now? Okay, great.
So this is.
This is great. We're all figuring this out. Okay, so now we should have just female. It should just say female and no F's and no capitals. Right? And we needed to do that because the next thing we want to do is to create a subset of the data. We want to take a portion of the data and we want to stick it in a new object, and we're going to call it female heights. And that's what this next line of code here does. It subsets the data. And basically it says take class data and look inside the class data sex column. And if it is equal to, and we use two equal signs because we're looking at a categorical variable, if it is equal to female, then give us the height. Then give us the height column, right? And put that in an object called female heights. And then what we get here is a data frame called female height. And it just has this one column called height, and it should just have the females. We also have a few missing values. Okay, now raise your hand if that's not working.
Sorry, Professor, can you go back and show how you got that female height into the environment tab?
Just run this code. Run this
Okay.
line. Run this line, and it's going to create a new object called female heights. Run this whole line. Now, thanks for asking, by the way. It's better if you ask now because these little glitches at the beginning, they'll make it so you can't go on. So you have to fix it at the beginning. That's what this class is for. We're for figuring it out. Did that work? Yes. Okay, good. Just give me a thumbs up if it's working. All right, now let's go on.
I don't like to see red.
And the next thing we can do is to calculate our summary statistics. We did this before. We looked at our summary statistics. So if we run this line, summary female heights, it'll give us in the console our summary statistics where it'll show height, it'll show our minimum, first quartile, median, mean, third quartile, max. And we can see right down here, we have 3 NAs. We have 3 missing values. Now, the thing about missing values is they can cause errors in the analysis later on. So we want to take those out. We want to take those out. That's part of data cleaning. So what we'll do is run this next line. See where I say, are there any NAs, missing values? I literally never seen that before, but I kind of guess there might be. Somebody's going to be absent, right? So this is a common problem. So let's clean that up. Run this next line. And all this does is it does this function called NA omit. Guess what that does? It omits the NAs for our object called female heights and sticks it back into our object called female heights. You run that line and then try again to calculate the summary statistics. And now you should not have any missing values. Raise hands if that didn't work out, got problems. Okay, as long as that works, super. Now that's the data cleaning step and the initial summarizing step. We can go on to making a histogram to check the assumptions of our data, right? You can also look at our mean. Our mean here is 161.8. What was our national average? It was the national average I put in here. Oh, I guess I didn't put it in here. I put it down here. It was 163. Pretty close. Okay, so let's look at a histogram to see if our data look normal. So we run this line and it gives us our histogram. If I make this window a little bigger, we can see it better. So I can see, hey, look at that. Our data do not look entirely normal. But it's probably going to be okay because the t-test is pretty robust to deviations from normality.
By running this, it should.
How many of us are in this little short people bin? It's like the short people bin and everybody else. Maybe if I wasn't in it, then it would be maybe not so bad. I'm just messing up the data, you guys. I'm sorry. I should take myself out of it. Okay. So the histogram is one way of looking at normality. Another way of looking at normality that we talked about before is by looking at the QQ plots. So to make a QQ plot, we can look at the QQ norm. And what this does is it plots our data in relation to, maybe I should do it like this. There we go.
Professor,
Yes.
I'm sorry, but for the thing on the console, my numbers are different from for the max. It doesn't, mine is different. It's not 176.7.
That's not your max.
Yeah,
Huh.
even
What's
though
your
I ran.
mean?
You might have
Um,
downloaded it at a different time.
Yeah, if you
150.
downloaded it a little bit before or a little bit after, then how many observations do you have for female heights?
It's 9.
Oh yeah, no, you only have 9. You got to re-download your data and re-import it. Sorry. You should have 17 observations.
Okay.
You Oh, did you download it today? If this is the same data that you downloaded earlier today, people didn't finish filling it out until right before we started doing this.
Okay, got it.
Okay, but practice those steps again. Thanks for asking. So the QQ norm plot, but what this does is it gives you the theoretical quantiles and your sample quantiles. And what you'd want to see is a straight line. This next line of code will show us what the straight line should be. So the dots should follow more or less this straight line, which they kind of don't, which is okay. We're just going to go with it anyway. Right. Well, let me look at some of this. So remember that if you go to code and you say soft wrap long lines, you'll be able to read the whole line of, and since I have really long comments, you might want to do that. So there's also a normality test we can use. The normality test is sensitive to sample size, and some statisticians say don't use the normality test. This isn't really the way forward. Just look at the QQ plots. Some people love the normality test. We're going to run it here so you can see what it is. So if I run this test, this is the Shapiro-Wilks test of normality. It kind of gives us a nice cutoff instead of looking at the histograms and saying, yeah, well, maybe, or looking at the normal QQ plot and being like, yeah, something like that. It gives you a p-value, and a p-value is a nice cutoff. You can say, well, if it's less than 0.05, then our data are not normal. If it's more than 0.05, our data are normal. And that's a very comforting kind of sense of certainty that we get from it. So if we run that test, we find that our p-value is more than 0.05. So at an alpha of 0.05, it's safe to assume that our data are normal. They're normal enough, right? Again, I explain it here in the comments. In this case, a p of greater than 0.05 is good. The data are fine. That means we can go on to calculating the t-test values. And I'm going to run it through kind of step by step here so you can see what happens in the calculations, even though R will just do it for you in a snap too. So to calculate the test, the t statistic, the test statistic, what you do is you calculate the difference in means of the sample versus the population divided by the standard error. Pretty simple, right? The first thing we need to do is get the mean value. We already did that in the summary statistics, but now we're going to do it again and store it in something called mean height. So we run this code here and we see mean height will give us the mean of the female heights height column. And our mean height here is 161.75. Everybody get that? Pretty close, I hope. 171.5, 161.5. 0.75. And the difference between the mean height of our sample and the mean height of the larger US population is something we calculate down here. This is going to be the difference in height, and that's mean height minus this population value of 163.54, just doing subtraction and storing that in a value here. So the difference between our height and the mean height of the national population is 1.78. We're about 1 3/4 centimeters shorter, which isn't a lot. It's like that much. It's not that much. It's not even an inch. So let's see, is that a significant difference? Right? Depends on the variability of our data. So now let's calculate the standard deviation and we'll be able to figure that out. So the standard deviation of our height is 6.5, right? That's a pretty good standard deviation. And the n, so the number of samples, we get that by this command length of female height. And that's going to store it into a variable called n height. So if we run this, we see we've got 17 observations, which is what we found before. Jesselyn, you got 17 observations?
I'm still working on it. I started from the beginning.
Started from the beginning? Okay. Let me know if you need help later on, but just go through it fast. Is it working?
Okay.
Yeah, okay,
Yes.
good. Okay, good. You should have 17. And then to calculate the standard error, we just take the standard deviation divided by the square root of the number of samples divided by 17. And it does it right here, and we'll store it into something called standard error of height. Is standard deviation of height divided by the square root of the number of samples of height. Run that line, we get our standard error is 1.5. So to calculate the test statistic, remember, we just take the difference in height divided by the standard error, and we'll put that in here as our t-value. So our t-value is negative 1.12937, right? Or we can just say negative 1.1. I think that looks like a pretty small t-value, and I'm going to guess, based on my experience, that that's not going to come out as significant, but we can go ahead and run this in R. I'm not going to make us go to the lookup table and, you know, the C table and figure out based on our degrees of freedom of 16 and our confidence interval of 95, like what's our critical t value. We're just going to run it in R and it'll give us the p-value. Okay. So here to run this test, it's t-test is the function. We put in the variable from our sample, female height, and mu, which is the population average, again, is 163.54. And we're going to store the results in this object called t-test underscore height. And then to look at it, we run that and we can see here, this is the result of the t-test. We can see it first tells us one sample t-test. Data, female height. That's what we told it to do, so that's good. The t statistic is negative 1.1293. Hey, isn't that what we got before? Yeah, looks like we did it right. Degrees of freedom, 16. Again, degrees of freedom is n-1. We had 17, so 16, that's right. And the p-value here is 0.2754. And that p-value is greater by kind of a lot than 0.05, which means that we fail to reject the null hypothesis. There is no difference between the female class height and the national class height, right? The difference was too small and the variance was too large to be able to say there was any kind of a real difference. Even though the mean was a little different, it's not different enough to be significant, right? And this gives us our p-value, which we already saw. Yeah. So now to calculate the confidence intervals, so that we can report our mean as confidence interval, or as mean plus or minus 95% confidence intervals, we can use this code down here. And what this is going to do is going to take the confidence intervals from that t-test we ran in R. It's going to pull out the confidence interval that's stored in that object and put it into something called confidence intervals of height. And when we do that, if we look at just this object, you can see that it contains two numbers. It contains 158 and 165. That's the confidence interval range. So the mean value ranges from 158.4 to 165.1. That's the 95% confidence interval of our mean value of 161.75, right? Now we want to take that lower confidence interval and that upper confidence interval and extract them as separate numbers. So what we do is we say that CI height, right? This is where we put our confidence intervals, square brackets 1. And what that does is it takes object thing one from that object and puts it in another object called CI low height. And you can see there it is, 158.4. It takes that lower confidence interval and puts it into CI low height. And part of the reason I'm showing this to you now is so that you see a little bit more about how to use this tool of the square brackets to extract things out of data objects in R. And we can do the same thing to get that second value, the upper confidence interval, by putting that CI underscore height and the square brackets 2. We said take thing 2 out of there. Take thing 2 out of there and put it in this new object. So it isolates it by itself, and now we can do math on it easily. Then we're going to take the mean minus the confidence interval, and we get 3.35. So that's our margin of error, right? That's our margin of error. We would say, or if we take the same thing, mean plus the confidence interval, it's the same. It's the same. So the confidence interval is symmetrical on either side of the mean.
It's giving me an error.
So if we to report the standard error, report the mean as 161.75 plus or minus 3.3595% CI. Report the mean as 161.75 plus or minus 3.3595% CI. This is how you could put it in a scientific paper. Okay, quickly, let's do some graphs here. So if we want to look at a histogram of the female height again, but this time we want to put a line at the sample mean. Here's our sample mean, is at the blue line. Now, what if we draw a red line at the population mean? Well, you can see they're really not that different. They're pretty close to each other. They're not significantly different according to the t-test. And then we can draw green lines around that confidence interval. And you can see that the confidence interval, of course, it contains our sample mean. It also contains the population mean. And that's typical. If a population mean is not different from a sample mean, it will be contained within the 95% confidence interval. So you see that here. Our 95% confidence intervals contain that population mean. It's not different from our sample mean. Right? Does that make sense? Now, if we want to make a nice bar graph that we could use for our publications to show how we compare with the national average, this is where we're going to load ggplot2. You should have it already installed. If you haven't already installed it, do it now. Use this install packages ggplot2. If you have installed it, then this library ggplot2 should work. I get an error message, but that's fine. It's still going to work. It just was built under a different version. And then we first have to make a new data frame to graph our data. Right?
Show me what you just made.
So what we're going to do is we're going to create a new object called bar graph data. And this object will be a data frame. It's that kind of an object where it has multiple columns and rows combined together. And we're going to have a group. The grouping value is going to be class, as in class average, and US, as in US average. And the mean height will be equal to the mean height from our class, which we calculated up there in the code, and the mean height from the national average. The confidence interval for the lower confidence interval is our CI low height that we got earlier, and 0, because we don't have the confidence intervals for the national average. Maybe if we looked up the paper where they calculated it, we would have it, but I didn't do that. I just pulled this off the web, so I don't have any confidence intervals. I just have that average. And the CI upper is, again, this is our class upper confidence interval, but we don't have a confidence interval for the US population. So we run this whole thing. I select this whole thing, make sure you got that last parentheses, and run that, and that will create a new little data object called bar graph data. And if you look at it here, it's got group, class us, mean height, class, not us, US, and then the upper and lower confidence intervals for our class. If you go back to our code, now we can use that little tiny data frame we made to plot the data in ggplot, and it'll make a really nice little plot. If you just put the cursor at the beginning of this big block of code and hit Control Enter, it'll go all the way down to the bottom and run everything for you. And what we get here is a bar graph with nice labels, and it shows us that our class average here in pink is 161.75 for mean height, and the mean height for the United States is here in blue. They look really similar, right? They weren't different from each other. That's what we found. Not surprised, not surprised. And you can see these bars here on the class, this little barbell looking thing, little exercise barbell looking thing. This represents the 95% confidence interval. This lower line here is the lower confidence interval, and the upper line is the upper confidence interval. How's everybody doing so far? Good? Okay, so if this works for you, copy image, I think that works. Let's go back to our lab, and we can paste our graph here. But we have to do a few more things here. Let's get control graph here. I forgot we need to do a few more things in this lab. So to calculate the test statistic, we put in again the sample mean, 161.75, and the population mean, which was 163.54. And divide that by the standard deviation. Where was our standard deviation again? Our standard deviation for height here was 6.5. 6.5, close enough. Divided by the square root of n, square root of 17. And our test statistic, and I'm not going to make you do the math. You can just go back to where we calculated our test statistic. And our test statistic was t-stat height, negative 1.13 if we round it. Negative 1.13. Okay, I did that kind of fast. Is everybody with me on filling out the worksheet? No. No, okay. So what I did to fill out this worksheet is I took our sample mean that we got in R, right? You look at R, we calculated our sample mean. Here is mean height. So if we run this line again, you go down to the console, and here's our mean height, 161.75. Just plug that into the worksheet here. On this line, that's our sample mean, right? And then we put in our population mean, because the t-stat is sample mean minus population mean. It's a difference in the means. And our population mean was 163.54. That's what I got off the interwebs. Right? And that's divided by our standard error, which is the standard deviation. And where did we get standard deviation? Well, we calculated it over here in R. So you go back to our R and you see where we said calculate standard deviation. We already did that. If you run this line again, you see our standard deviation was 6.51, 6.5, close enough. Go back to our worksheet and put in 6.5. Divided by the square root of n. I'm not actually going to calculate the square root of n. I'm just going to say, put n here, square root n. Delete some of those lines. And if you did this math, the sample mean minus the population mean divided by the standard deviation, which is then also divided by the square root of n, then you would get our t-stat. And our t-stat is negative 1.13. And if you go back to R, you can verify that by looking both here at our t-stat, where we say calculate test statistic. T-stat for height is negative 1.129. So I rounded it to 1.13. Or if you look here, when we did our t-test using the t-test function, when you look at the results of that, you also get the test statistic here. You with me? Yeah.
You can also just look at the values, yeah? In the upper right hand quadrant.
The values in the upper right quadrant.
It saved all of that data if you want to look at all of it, you know, under.
Yeah, it's also here. Yeah, that's right. That's right. These are all right here. That's right. You can look at it right here. It's all the confidence intervals, the height, the difference. You're right. It's all up here. You can just look at it. Right? There's our mean, there's our difference. There's our t-stat. It's all saved right there. So you can just take the values out of here. Thank you for pointing that out. Just trying to drive home to you that this t-test isn't really that complicated. I mean, this is really just basic math, right? We're taking the square root of something. That's probably the most complicated thing we do. Otherwise, this is basic arithmetic you've probably been doing since grade school, right? But now we're using it to make inferences about a population. So we're using this basic math in a neat way, in an applied way. The next thing I want you to do is paste your graph here. Paste your graph here. And this is just the graph we just made. You can make it smaller if you want to, so you can kind of see all of it. That's your graph. That's the graph we made. And then interpret the results. So here I gave you an example of how to write your results in the appropriate sort of APA scientific format. So the example would be, there is a significantly higher depression score with placebo than caffeine. Open parentheses, you write your t-stat, comma, degrees of freedom, comma, p-value. Thus, caffeine appears to be an effective treatment for depression, right? Some kind of biological conclusion. Now, if we were to do this for our little study that we just did a scientific study. We collected and analyzed the data. We ran through the whole thing in like an hour. Kind of amazing. We could say, what? How are we going to say here?
There's no significant difference.
We can say there's no significant difference. Yeah. Or we can say that our biostats class female heights are similar on average to the US national average of female heights. I mean, we can put it as there's no significant difference. I just try to phrase this more in terms that are more, I don't know if I would say conversational, but just plain English, right? Our biostats class female heights are similar on average, commas there, to the US national average of female heights. And you could say then you open that up and then you put our t-stat. Where was our t-stat? Our t-stat is negative 1.13, right? So we say T equals negative 1.13, comma, DF, degrees of freedom, was equal to 16, right? Because we had 17 samples, n minus 1. And then our p-value, what was our p-value again? Our p-value. What's that? Oh, here it is 0.2754. Right? And so what would we conclude from that? Or we could say our biostats class female heights are, we get more information, is 161.73 insert symbol plus or minus, or our mean height for our biostats, our mean female heights for our biostat class.
Thank you.
I gotta edit this a lot. Our mean female height for our biostats class is 161.75 plus or minus, what was our confident? 3.35 plus or minus 3.35, which is similar to the US national average of female height, which was it 163.54. I try to get as much information in there as possible, right? Look, now we got all that in there. Say, okay, we talking about us, we're talking about female, we're talking about height. Look, we just put our average, and we better say what this plus or minus means. Plus or minus 3.35, 95% CIs, right? Otherwise, it could have been standard error. People use different things for that plus minus, which is similar to the US national average of female heights, 163.5, right? That's a nice conclusion. What can we say? Well, thus we are a representative sample of Americans, something like that. Thus, our class appears to be a representative sample of American females. Right? Hey, cool. Okay, now I want you to, you know what, you guys, I don't think we're going to have time to do all this. I don't think we're going to have time to do all this with a different thing. You know what, you guys, if you turn this in just like this, that's going to be okay. That's going to be okay. But in the next 15 minutes, I'm just going to kind of walk you through how I would do this, You can just follow along with me. I wanted you to go and find another average and run through this on your own, but I'm just going to say we only have about 8 minutes left, and that's probably enough time. So I'll just do this with you. So when you do send in your lab report, I want to give you an example of how I want you to do it, right? So I want you to start off with a header. Your header should be something like, national versus class averages for female height. HEIGHT. Right? That would be the study title. And then, you know, my author Faith Inman, right? And the date, this is like our title, author, date. This is the 25th of January, 2024, right? And then your introduction, a brief background of the study. What's a brief background of the study? We want to say something like, why would height matter? Why would height make a difference? Maybe we say something like, human height is an indicator of health, right? And nutrition. Just spoiler alert, I looked that up. I found a paper that talks about that. And thus is of interest to compare among regions. Or you might come up with something else. You might come up with something like, the people in Hawaii tend to be of a different ethnic makeup than most of the American population. Therefore, we might expect our heights to differ. You could say something like that, right? And then you say include at least one reference. The national, or maybe because this was from 1996, humans are getting taller over time. So we expect and the national average of human height for people born in 1996 may be shorter than our class average because our class average birth year is later than that date, which I didn't actually calculate, but I think you guys are almost all like 19 and 20 and 22, right? So you're born after 2000. Maybe that's not a big enough difference. And then you state the study question, right? Or just take it from up here, right? We've got it up here. We've got our study question. We already did that. Is the average height of female students in our class different from the national average, right? So we wanted to know, we conducted this study to determine if the average height of females in our class differs from the national average as stated on World of Data. And here's where you cite your reference. And, for the sake of this kind of thing, I'm totally fine if you just give me a web link. Although later on, I will require you to give me citations in APA format. Right? Our null hypothesis is, and then you can just put in the null hypothesis from above, and our alternative hypothesis is, and you can put in our null hypothesis from above, right? Simple. That's what your introduction will look like when you do these reports. This is what I want you to write, something like that. And then the method, simply explain what we did. We recorded the height of all female students in our class. Well, we could say of all students in our class. Because we included the men, but we had to take them out later to get the average of all students in our class, and found a national average online. We conducted a one-sided t-test to compare the sample and population means using our statistical software, right? And then you should cite R. How to cite R. Well, we don't have time to look that up, but I'll show you later. And then the results, this is where you put in the tables and graphs and exactly what we did, exactly what we set up here. Our mean net female height. This would be our results. This would be our results section, right? This has to be down in here. And this is also where you would put the graph. And when I say give me the one sample t-test result outputs from R, it can just be this. It can be this right here, okay? And then the discussion conclusion, what do we conclude about our data? How do we differ from other populations? Do you offer any reason why we see patterns in these data? What further research could we do? Okay, we don't have time to get into that, but you can think about this for yourself. So turn this in with all of this filled out as much as possible. And 2 extra points if you write me a nice discussion. Okay, Michelle, give them 2 extra points if they write me a nice discussion.
Okay. Double checking, they have until the 26th at 11:55 to turn it in.
No, that's the resubmission. Sorry, no, that
Okay.
I'm not sure how that shows up like that. That's not right. No, they are supposed to turn it in by tomorrow night.
Yeah.
Yeah, 26 says due 20. Oh, accept resubmission. Okay, sorry. Let's be clear. The resubmission is if there's a problem
Mhm.
and they turn it in on time and you give them feedback
Mhm.
and they work on it some more and they send it back in, that's the deadline for that.
Okay.
Yeah, that's for resubmission. That's after they turn it in and you're like, hey, look, I can see there was an issue, or maybe there was just some kind of an issue. Like sometimes you somebody submits the wrong thing, they upload the wrong file. It happens. That's just to give you that little extra fudge time to fix things, but it's due tomorrow night.
Okay, perfect.
Yeah.
And also, yeah.
Are we doing a whole other research question of our own?
No, you don't have to do a question of our own. I thought we would get further. I thought we would go further faster and that you would have at least 20 minutes in class to just do that on your own and kind of run through it. But just turn in what you have. That's fine. You don't have to
Yeah.
do your own question.
And I just want to show them a quick thing as well. So with how to know when to run it as a chunk altogether versus line by line, if you see here, there's an indentation. That lets you know that it wants everything underneath. So those indentations let you know to run everything.
Yeah, like this will run. This whole thing will run.
Yeah,
This whole thing will run.
that's a hint for select one. Yeah.
Yeah, good. Thank you for pointing that out. That is very helpful. Wow, we did a lot. We did a lot. Bravo, you guys. Bravo. And have a fantastic weekend.